So in section 2, we're dealing with infinity in limits, but this was exactly the same rules as we had in section 1 that I said, these rules are exactly what they think they should be. If we have a function f and the limit is L1, and we have another function g and the limit is L2, we put infinity here. Well, it wasn't infinity there before. It was as x approaches c. But the rule is the same. If I'm taking the limit of the sums, it's just the sum of the limits. So in other words, it's just limit of f of x plus limit of g of x. And limit of a difference is just the difference of the limits. We can sort of distribute that limit, even over multiplication. Limit of f times limit of g. Okay, so it's exactly the same rule. So it's that rule that's like, man, I hope that's what the rule is, because otherwise I'm going to have to memorize it. This one just makes sense. You all good there? Okay. You heard me talk about M-model behavior last year. It's also just called N-behavior model. Either way, our book calls it N-behavior model. I kind of like N-model behavior. I'll be guilty of that. It's just what happens when X gets really, really big, and it's really easy to analyze in many, many cases. Okay? Again, you can look through this if need be, but I don't think the need's going to be after we go through some examples. We're going to be dealing with horizontal and vertical asymptotes. Again, you can look through this if you need. Notice when they're talking about limits can be infinity, they're always talking about left or right-hand behavior. They're not just saying the limit of A can be infinity. The limit at A, it's always left, right-hand behavior. Here's a good one, kind of a reminder to us. Let's look at these bottom ones. If we have a rational function, and what is a rational function? It's a polynomial on a polynomial. For rational functions, if the degrees of the polynomial are equal, so let's say I have 2x to the third plus 7 over 5x to the third minus 2x. They're both third degree. Then we have a horizontal asymptote. And they say it's y equals k, but it's the lead coefficient over the lead coefficient. If that doesn't make sense to you yet, it's going to when we turn the page. If the degree of the top is smaller than the degree of the bottom, let's say I've got second degree over third degree. A second degree, if I put 1,000,000 in, I get 1,000,000 times 1,000,000. Big number. The denominator, I get 1,000,000 times 1,000,000 times 1,000,000. 1,000,000 times bigger. Way bigger than this. The numerator outpaces the denominator then, and we have and the limit would become 0 at that point. We're going to get closer and closer to 0. If it doesn't make sense, it will shortly. And if the degree of the, stay here, if the degree of the numerator is bigger than the degree of the denominator, like third degree over first degree, there's nothing to keep that third degree in check. It's either going to approach infinity or negative infinity, depending on the sign. But all of this is going to make sense when we go through some examples. I'm going to overkill a couple of these with graphs just to kind of review graphing rational functions. So we have this function y equals 2x plus 3, and we're supposed to use algebra to find the limits defined by the expression. So I want to find the limit of y as x approaches infinity. And here's our big x test. What happens as x gets huge? If x is 1 billion, I've got 2,000,000,003 in the numerator. You give me $2 billion, I'll throw $3 in the street. That 3 doesn't really matter when we get big. It matters just enough to keep us from arriving. Over 5,000,000,007. If we had to approximate 2,000,000,003 divided by 5,000,000,007, we'd say it's 2/5, right? So we just, here's the approach when it's polynomial. We say 3's not really a player in the numerator when x gets big. 7's not a player in the denominator. So I get 2x on 5x. The x's cancel. The limit as we approach infinity is 2/5. So if we were going to graph that, we would have a horizontal asymptote at 2/5. Now, you don't really even need to put the dotted lines in near 0 because it really only happens when x gets really huge, positive or negative. We're going to get sucked into this thing eventually. Okay? How about when we put in negative infinity? How about the limit as x approaches, and I kind of implied it here, negative infinity of y? Well, it's still 2/5. It just happens to be a negative over a negative. Cancel the x's, it's still 2/5. So you might be thinking, oh, well, it's always the same in both directions. Not going to be. Not always. Okay? Then if we were going to graph this, and we'll practice some of these on the next page, we'd probably set 2x plus 3 equal to 0. You don't need to write this down. 2x plus 3 equal to 0, and we'd get negative 3/2, so we'd have a point down here somewhere. And then we'd set the denominator equal to 0, and we'd get negative 7/5, and what would that tell us? Can the denominator be 0? No, we can't have the denominator 0, so negative 7/5 is out of bounds. So negative 7/5, we have another asymptote over here. And we probably expect some kind of curve in one of these translated quadrants. Is that okay? All right, but they're not even asking for all of that right now. They're saying, what is the limit of this as x approaches infinity? And we say big X's. The 1 and 3 don't matter much. They just keep us from getting on top of the asymptote. But they don't matter much. So this wants to act like the limit as x approaches infinity of x on x squared. I shouldn't even put equal, because it's not quite, well, actually the limits are equal, but these guys aren't equal. And that's 1 on x. And 1 on x, when x is a billion, is 1 apple to feed the world. Everybody gets nothing. The limit of this is 0. Now there's a rule that says, oh, if the degree of the denominator is bigger than the degree of the numerator, then it's going to be 0. And you can memorize that rule, but understanding the big X test, I think, is pretty easy, instead of memorizing 3 different rules. Is that okay? How about when we approach negative infinity? Well, negative infinity, it's still going to be negative x on positive x squared, but the x's cancel and I get negative 1 on x. Negative 1 on x is still going to be 0. Here's the only thing we gain from that, talking about the signs. If I was to graph this, and I put in a huge positive, I get positive on positive approaching 0. It's approaching from here. If I put in huge negative, I get negative over positive, right? When I square it, negative over positive is negative. It's approaching from under here. So that's a little bit useful if I had to graph it. Is that all right? Okay. Let's go limit as x approaches infinity. When x gets really huge, the 6x doesn't compete with the 3x squared, so it's relatively insignificant. The 8's insignificant. I get 3x squared on 4x, or basically I'm finding the limit as x approaches infinity of 3x squared on 4x, or 3x on 4. Well, as x approaches infinity, I get 3 times infinity on 4. This is infinity. It's going to go up forever. Now, this is overkill. If we were going to graph this guy, we might want to talk about the slant asymptote. I have a second degree equation divided by a first degree equation. A result will be a first degree, right? In fact, I could even say this. It's going to have slope 3/4. The asymptote on this is going to have slope 3/4. It's just, is it 3/4 up or down? Or is it 3/4 at 0? How do we find out where it's at? Anybody remember from last year? This is just a division problem. Again, this is a little bit overkill for what they're asking right now, but it's something we need to talk about at some point. Well, this means 4x minus 8 into 3x squared minus 6x plus 0. 4 times what equals 3? Well, I got to cancel 4, and I got to introduce 3. X times what is x squared? X. So I get 4x squared. Let's see. I get a minus 4 and a 8 and a 4 reduced to minus 2 times 6 minus 6 with an x. Ooh, that's good news. We're subtracting these, remember? Oops, this will be minus, sorry. And that's 3x. Yikes. That's good news. So we end up with just 0. So our slanted asymptote would just be up 3 over 4. Okay. Is it the same when we put in negative infinity? Let's see. Limit as x approaches negative infinity. That would still reduce to 3x on 4. But if I put negative infinity in here for x, I get negative infinity. Oh, that's kind of what I thought. It's going to get sucked into this asymptote and go down forever to the left, up forever to the right. Okay. Take a look at D. Do you know our end model behavior, or our end behavior model right now when you look at D? Is this jumping out at us? 2x doesn't matter, 3 doesn't matter, 3x squared doesn't matter, 5x doesn't matter. Eventually this is going to look like negative 2x cubed on 3x cubed, or negative 2/3. There's a rule, but I'm just using big X test. Limit as x approaches negative infinity, does that change anything? No, the x cubed still cancel, and I still get negative 2/3. So oftentimes they're the same. Certainly if it's a horizontal asymptote, they're going to be the same. Any challenges on E? Limit as x approaches infinity. I got 1 apple again to feed the world. Everybody gets nothing. What's that mean on our graph if we were to be graphing it? It means on our graph we've got a horizontal asymptote right here. Is negative infinity going to change that? No, it's just 1 on negative infinity to the 3rd. So plus minus both ways. What would change is, as I go to the right, I'm going to get 1 on a positive. As I go to the left, I'm going to get 1 on a negative. Let me see hands if this seems very, very familiar. Yeah. Okay, good. Didn't waste our time last year. Okay, find the following limits by a convincing method of your choice. Oftentimes in that case, if you know much about me mathematically, I'm going to probably look at graphs. So this says, find the limit as x approaches 2 from the right. If we're going to graph this guy, things I'm going to do. I'm going to set the numerator equal to 0. Well, 1 can't be 0. The only way a fraction can be 0 is if the numerator is 0. So we're never going to hit 0. We're never going to hit 0. Doesn't mean that's an asymptote yet, but it might be. We're never going to hit 0. I'm going to set the denominator equal to 0. Oh, we cannot be 2. No wonder we're finding a limit there. Now, if they just asked for the limit as x approaches 2, and not 2 from the right side, we'd be done. We'd say there is no limit. But from the right side, we need to know what it's doing. Okay, and then I would just maybe start thinking about picking some points, and the easiest point to pick is when x is 0. If x is 0, I get 1 on 0 minus 2, negative 1/2. And truthfully, that is enough for me to know what's happening. Any chance this is going through this asymptote? Oh, didn't talk about asymptote. Big X test. X gets huge. 1 on huge 0. So 0 is an asymptote here. Any chance we pass through the asymptote? Do we ever pass through horizontal asymptotes? Stay tuned. We did last year too, once or twice. We're going to again soon. But we're not going to here because I know there's not a 0. There's no... Think of this. If we can make the numerator equal 0, that value is like a manhole on the street to the sewer. You can pop up and go through there. We don't have any. We can't make... Like in this one, 0, we're going to get to pass through. Got a little manhole cover at 0. Not here. So I suspect this thing looks like this. But I better figure out what it looks like when I get on the other side. If I put in 3, I get 1 on 1. And that is enough for me to know I'm not going to hit this asymptote because I can't go through 0. The 1 is never equal to 0. Now can we answer the question? What is the limit as we approach 2 from the right? So I'm approaching 2 from the right. When I'm getting close to 2, I'm getting close to infinity. Or I'm approaching infinity. You don't ever get close to infinity. Okay. So this is infinity. We won't answer infinity for a plain old limit. But right hand, left hand, we can answer infinity or negative infinity. Clearly our left hand approach to 2 would be negative infinity. Is that okay? All right. Let's quick sketch of this guy. Once again, vertical asymptote at 2. What happens when x gets huge? This function wants to become what when x gets huge? 1. Wants to become 1. Is that all right? Let's set the numerator equal to 0. Oh, that just gives me x equals 0. So 0 gives me 0. Denominator was equal to 0. We got our big x test. Is there any other passageway through 0? Can I get through the x-axis any other way than going through it at x equals 0? No, the only solution up here was 0. Am I going to bounce off of that? Nope, it's just a first degree 0. This thing has to look something like this. Now, A or B, I'm going to say that for a while. A or B. Anybody have the eye doctor by, I asked you guys this last year. Anybody have the eye doctor by Highlander? That's my imitation of her. A or B. If you have her, you know what I'm saying. 6 or 7. Right, Sierra? Yep. Where am I at? Up in A, down in B? Or should we put 3 in and find out? You can put 3 in, I don't have to. I know where we're at. If I'm in B, I got to cross the x-axis, and I can't cross the x-axis over here. There's no more zeros. I'm somewhere like this. What happens is we approach 2 to the right. 2 from the right, we're approaching infinity. Is that okay? Again, you could pick 3 and get that point and then fill it in. But I knew there was not a manhole cover to get through over here. All right? Virtually the same, and I think they're trying to make a point when they get to D. All right. Set the numerator equal to 0. Oh, can't be. Set the denominator equal to 0, negative 3. Oh, we can't have x be negative 3. What happens when x is huge? 1 on infinity wants to be 0. Set x equal to 0, 1/3. Okay. Is that all right? Now, where am I, down here or up there? Don't know now. So maybe I would put in a real quick test at negative 4. Put in negative 4, get 1 on negative 1. So, is that right? Did I do this right? Put in 0, get 1/3. That's terrible. How come you guys weren't yelling at me? Put in 0, get 1/3. Not down here. Put in -4, get -1. Down there. What's happening is we're approaching -3 from the right. Infinity. -3 from the left. Negative infinity. My apologies on that. Is that okay? I put in 0, should get positive 1/3. And D. Set the numerator equal to 0. 0. Got a point there. Set the denominator equal to 0. Denominator can't equal 0, so x can't equal -3. Big X test. What's this graph eventually want to look like? 1. C or D. We could put -4 in, but we're in C. Don't know why I did that in black. But we're in C because there's no passage through 0 outside of right there. Right? No manhole cover here. The only way to get from the sewer to above ground was right there. So I couldn't be down here and get sucked into that asymptote. So what are we doing as we are approaching -3 from the right? We are approaching negative infinity. I think what the author is trying to get across here is, oh, infinity, and what do? We just basically change this, put an X on, change this, put an X on. Be careful if you start thinking that those patterns are just always going to hold for us. Okay? Alrighty. Now we actually are supposed to do some graphing here. So find the end behavior asymptote. What's it going to look like eventually? Let's just stop right there. That is saying what's going to happen when x gets really, really huge. 2 doesn't matter. 5 doesn't matter. 3x doesn't matter. X cancels x, and I get 1 on 2x, and that's 1 on 2 times a trillion. 1 on 2 times a trillion is virtually 0. It wants to be 0. So y equals 0 is our horizontal asymptote, or our end model behavior. Now, I could even do this little extension of that. If I put in a huge positive, I get positive on positive. So I want to be 0 from the positive side. If I put in a huge negative, I get negative on positive, right? When I square it, that one wants to be a negative. So I know I'm down here. That's kind of helpful. It only takes a second. See what I'm saying? All right, let's set the numerator equal to 0. What's that give me? 2? 2 is the only place I can go from the sewer to the street. Okay. Right on the asymptote. Horizontal asymptotes are about what happens when x gets huge. We're going to get sucked into this thing eventually, which means I'm either crossing and getting sucked back down into it, or I'm crossing down and getting sucked back into it. In fact, horizontal asymptotes can get crossed an infinite number of times. If you imagine a diminishing sine curve, so something, let's just say it wiggles, it's getting sucked into that asymptote, but it's constantly narrowing its search. So horizontal asymptotes can get crossed, not vertical. Okay. Next, how about denominator equals 0? Well, are there factors, otherwise I got to do a quadratic formula, of -10 that add up to be +3? +5, -2. So to get a -2, I'm going to go 2x here. You guys might do this a little bit differently. A -1 there. I'm going to go a 5x here. Nope, just an x there, sorry. And a +5 here. So x cannot be 1 and x cannot be negative 5 halves. It's negative 2.5. What would have happened if what would have happened to the graph if one of my factors was an x minus 2 here? Remember? Yep, there'd be a hole in the graph at 2. So we just draw along and then have to put a hole wherever we hit 2. Okay, so that gives me a fair amount of guidance. How about when x equals 0? Look how easy this point is. X equals 0, I get 0, 0, 0, I just get negative 2 on negative 5. That's 2/5. At 0, I'm up at 2/5. All right, what do you think? Comes down, touches, comes down, comes up, touches, goes up, or comes down, touches, goes up? Only one of those makes sense. It's the only passage. It's the only way I'm getting through there. That's the only place I can hit 0. I don't know exactly what this looks like. I don't know exactly where it reaches the bottom, but it's got to look like this. I can't pass through another 0. The only 0 is at 2. Is that all right? Okay. Now, if I know this ends down here, if this ends above, then this must come through here. I don't know how high it goes. It must come down there. If I want to know how high it goes, I would maybe put in 3 and 4 and find out where it goes to. You with me? How do I know it doesn't do this? Come down, touch, and go back up. If this was like this, that might be the case. But it's not going to act like a parabola there. It's going to act like a line that just passes through it. That's a linear 0, just pretty predictable. Again, I don't even think it goes that high. You can check. If this is down here and there's no passage through, doesn't this part of the graph look something like that? Maybe it gets closer, but we got the general shape right. Okay? All right. So we've got our behavior asymptote right here. That's our end model behavior, y equals 0. Find all vertical asymptotes. So our vertical asymptotes, I guess I'll label these y equals 0. Here's x equals negative 5 halves, and here's x equals 1. Our vertical asymptotes. Okay. Then, as far as where the curves fit, we would just have to do some t-charting there if we had to do it by hand. All right, same thing. So again, I'm going to set the denominator equal to 0. X cannot be 2 and negative 2. Right? Factors x plus 2, x minus 2. I'm going to set the numerator equal to 0. Are there factors of 15 that add up to negative 1? Nope. So we would need to quadratic formula that. Dot, dot, dot. How about end model behavior? What happens when x gets huge? When x gets huge, minus x plus 5 minus 4 don't matter. I get 3x squared on x squared, which is 3. Our behavior asymptote is y equals 3. Let's think about this just for a minute. This is just kind of fun to talk about. This graph goes through 5, right? How does it go through 5? Going up or going down as we move to the right? Going down at 45. And then it wants to be a really steep parabola, right? Do you think it's going to get down there? Think it's going to get down to 0? It's only going down at a slope of 1, right, -1 right now. That's not real steep. I bet you go quadratic formula on this thing, the numerator can never be 0. You can try to put that in quadratic formula, but I suspect it's never going to be 0, which means we don't have manhole covers here. Okay. I'm going to leave that for you to explore, and we will pick it up there tomorrow.